Good day, everyone. I am Czarah Beringuel from Group 5, and today we're going to discuss linear programming models, graphical method. For my part, I will discuss what is linear programming and what are its properties. First, let us define linear programming. What is linear programming? Linear programming, or LP, is a widely used mathematical modeling technique designed to help managers in planning and decision-making relative to resource allocation. Programming in the world of management has very little to do with computer programming. Instead, it refers to modeling and solving a problem mathematically. Linear programming is also used for obtaining the most optimal solution for a problem with given constraints. Now, there are 7 linear programming properties. Number 1 is that linear programming should have one objective function. Number 2, there must be one or more constraints. Number 3, there must be alternative courses of action. Number 4, objective function and constraints are linear, proportionality, and additivity. Number 5, certainty. Number 6, divisibility. And number 7, non-negative variables. We will discuss each of the properties in the next slides. So the first linear programming property is that it must have one objective function. Objective function is a linear mathematical relationship that describes the objective of the firm in terms of the decision variables. Decision variables are mathematical symbols that represent levels of activity by the firm. In the example below, our decision variables are the number of bowls and mugs to produce. Moreover, objective function always consists of either maximizing or minimizing some value. For example, based on the table, the objective of the company is to maximize the total profit. The company's profit is the sum of the individual profits gained from each bowl and mug. Profit derived from bowls is determined by multiplying the unit of each bowl by the number of bowls produced, that is, $40 times X sub 1. Also, profit derived from mugs is derived from the unit profit of mug, multiplied by the number of mugs produced, or $50 times X sub 2. Thus, total profit, defined symbolically as Z, can be expressed mathematically as $40 times X sub 1 plus $50 times X sub 2. Second, it should have one or more model constraint. Model constraint represents a restriction on decision making. For example, based on the previous slide's table, deciding how many number of bowls and mugs to produce every day is restricted by both labor and clay. So the constraints are labor and clay. Constraints also limit the degree to which we can pursue our objective. Third, there must be alternatives available to choose from in the problem, because if there are no alternatives available, then linear programming is not needed. For example, a company uses linear programming in deciding how to allocate the limited production resources among the 3 different products to maximize profit. So the company may choose to devote all manufacturing capacity to make only the first product, or produce equal amount of each product, or should it be to allocate resources in some other ratio. Next, objective functions and constraints are linear, proportionality, and additivity. Though written in the book is proportionality and divisibility, I think it should be additivity because divisibility will be explained later in the next slides. So the objective and constraints in linear programming problems must be expressed in terms of linear equations or inequalities. Linear mathematical relationships just mean that all terms used in the objective function and constraints are of the first degree. So the word linear implies both proportionality and additivity. Proportionality means that the rate of change is constant. This means that if a production of 1 unit takes 3 hours, then with 10 units, the production would take 30 hours. While additivity means that the total of all activities equals the sum of the individual activities. That is, if the production of one product generated $3 profit and the production of another product generated $8 profit, the total profit would be the sum of these two, which would be $11. The fifth linear programming property is certainty. This assumes that all constant terms, objective function, and constraint coefficients are known with certainty and do not change during the period being studied. Next is divisibility. Divisibility means that solutions are divisible and may take any fractional value, and there is no need to be in whole number or integers. In production problems, this implies a work in process. For example, a 0.3 chair. A 0.3 chair means that it is unfinished, thus a work in process. And lastly, the seventh linear programming property is non-negative variables, or the non-negativity constraint. This restricts the decision of the variables to either 0 or positive, since it is impossible to produce negative items. For example, we cannot produce a negative number of tables, mugs, and pants. It is usually expressed as x sub 1 is greater than or equal to 0, and x sub 2 is greater than or equal to 0, where x sub 1 and x sub 2 are the two decision variables.
Hello everyone, I'm Alfredo, and I'll be discussing the graphical linear programming method limitations and the summary of the graphical solution methods. For graphical linear programming method limitations, the graphical method works only when there are two decision variables. When there are more than two variables, it is impossible to plot the solution on a two-dimensional graph. The graph was usually plotted on the upper right corner, which all the positive numbers are located. For more than two variables, it results to more complex approaches, which provides valuable insight into how larger problems are structured, which uses more complex method to solve. Next, the following are the summary of the graphical solution methods. Number 1, problem description. 2, formulate a problem as a linear program. 3, graph each constraint equation. 4, identify feasible solution region, that is, area that satisfy all the constraints simultaneously. 5, select one of the two following graphical solution techniques and proceed to solve problem and find the optimal solution. You can choose isoprofit or isocost method or the corner point method. So let's try to solve this problem taken from the book of Render, focuses on the Flair Furniture Company. The Flair Furniture Company produces expensive tables and chairs. The production process for each is similar in that both require a certain number of hours of carpentry work and a certain number of labor hours in the painting and varnishing department. Each table takes 4 hours of carpentry and 2 hours in the painting and varnishing shop. Each chair requires 3 hours in carpentry and 1 hour in painting and varnishing. During the current production period, 240 hours of carpentry time are available and 100 hours in painting and varnishing time are available. Each table sold yields a profit of $70,000 and each chair produced is sold for a $50 profit. Flair Furniture's problem is to determine the best possible combination of tables and chairs to manufacture in order to reach the maximum profit. The firm would like this production mix situation formulated as a linear programming problem. So this table shows the summarized data from the problem that shows the hours required to produce 1 unit of either the table or the chair. To solve the problem, let's find first the decision variables. Decision variables was discussed by the first presenter. So for this problem, the decision variable that represent the actual decision we will make are defined as V equals the number of tables to be produced per week, C equals the number of chairs to be produced per week. So next is what is the objective of the company. As what I mentioned earlier, the company's objective is to maximize profit. Next, let's find the constraints of the problem. For this problem, the constraints are 1. The hours of carpentry time used cannot exceed 240 hours per week, or in other words, carpentry time used is less than or equal to carpentry time available. Or 4T plus 3C is less than or equal to 240 hours of carpentry time. 2. The hours of painting and varnishing time used cannot exceed 100 hours per week, or in other words, painting and varnishing time used less than or equal to painting and varnishing time available. Or T plus 1C is less than or equal to 100 hours of painting and varnishing time. D used less than or equal to, or the sign of inequality, because 240 hours of carpentry and 100 hours for painting and varnishing are the maximum limitation that can be used, not an amount that must be used. Next, values of T and C must be equal to 0 or positive values, and these constraints are referred to as non-negativity constraints, which means that T is greater than or equal to 0, or number of tables produced is greater than or equal to 0, and C is greater than or equal to 0, or number of chairs produced is greater than or equal to 0. While the non-negative constraints are technically separate constraints, they are often written on a single line with the variables separated by commas. Thus, T, C is greater than or equal to 0. The Flair Furniture Company problem may now be restated mathematically as maximized profit equals $70 T plus $50 C, subject to 4T plus 3C is less than or equal to 240 for the carpentry constraint, and 2T plus 1C is less than or equal to 100 for the painting and varnishing constraint, and lastly, and TC is greater than or equal to 0 for the non-negativity constraints. Next, let's graph each constraint equation. For the variable T for tables is located on the graph's horizontal axis, while the variable C for chairs is located on the vertical axis. The graph in the slide shows the axes represent the constraint T and C are greater than or equal to 0, which are the non-negative constraints of the problem. Next, to represent the first constraint graphically, we must first graph the equality portion of this, which is 4T plus 3C equals 240. To plot the line, find the 2 points that satisfy the equation, then draw a straight line through them. So, when Flair Furniture produces no tables, then we substitute 0 to the T, then 4 times 0 plus 3C equals 240, 3C equals 240, C equals 80. When a firm makes no chairs, that is, then we substitute 0 to C, then 4T plus 3 times 0 equals 240, 4T equals 240, T equals 60. Then graph it and draw a straight line. After plotting the graph, there are 3 possibilities that can be interpreted. First, any point that lies on the line satisfies the constraint, and any combination of tables and chairs on it will use up all 240 hours of carpentry time. Next, all the points on the left side of the line will likewise satisfy the constraint. And lastly, all the points on the right side of the line will not satisfy the constraint. For example, the point 30 and 20, which equal to 180, since 180 is less than 240, which is the limit, then this point satisfy the constraint, and all points on this side of the line will also satisfy the constraint, which is indicated by the shaded region. Then, for example, point 70 and 40, which totaled 400, which is greater than 240, which is the limit, then this point and every other point on that side of the line would not satisfy this constraint, for they would require more than 240 hours that are available. Let's do the same thing on the second constraint, which is 2T plus 1C equals 100, which limits the time available in the painting and the varnishing department. Solve for the corresponding points and plot it on the graph, which you can see on the slide, and all the points in the shaded region satisfy the constraint. Then, in a linear programming problem, we need to find the set of solution points that satisfy all the constraints simultaneously. Hence, the constraints should be drawn in one graph. As what you can see in the slide, the shaded region now represents the area of solution that does not exceed either of the two flare furniture constraints. These are called the feasible solution. Any point outside the shaded area would represent infeasible solution.
Hi, this is Czarah as Ylaya, and I'm going to talk about the different approaches that can be taken to solve the optimal solution when the feasible region has been established graphically. These are the isoprophet line solution method and corner point solution method. We will first discuss the isoprophet line solution method. There are 4 steps. First, graph all constraints and find the feasible region. Second, select a specific profit or cost line and graph it to find the slope. Third, move the objective function line in the direction of increasing profit or decreasing cost while maintaining the slope. The last point it touches in the feasible region is the optimal solution. Fourth, find the values of the decision variables at this last point and compute the profit or cost. First, we need to graph all constraints and find the feasible region. So the graph shown is from the Flair Furniture Company problem. And if you can remember a few minutes ago, you have already identified the feasible region, which is the shaded part. Again, the feasible region is the part where all the constraints overlap, meaning all the conditions specified in the problem's constraints are satisfied. Since we have already identified the feasible region, we can now select a profit line and graph it to find the slope. For the Flair Furniture problem, we may choose a profit of $2,100 when an objective function of $2,100 equals 70t plus 50c. To plot the profit line, we will do the same thing we did when plotting a constraint line. To find c, we will let t equals 0, and to find t, we will let c equals 0. So any combination of tables and chairs on the isoprophet line produces a total profit of $2,100. Clearly, the isoprophet line for $2,100 does not produce the highest possible profit. With this, we will proceed to the third step. Move the objective function line towards increasing profit while maintaining the slope until we find the last point that touches the feasible region. An important point is that all isoprophet lines are parallel. With this, we can just draw a series of parallel isoprophet lines until we find the highest isoprophet line, the one with the optimal solution. In the last step, we need to find the values of the decision variables at this last point and compute the profit or cost. To find the coordinates of this point, solve the 2 equations simultaneously. This will be discussed further in the next method. So looking closely at the graph, the last point that touches the feasible region is the point 3040, which is 30 tables and 40 chairs. We will now calculate the profit through the equation profit equals 70t plus 50c. We need to replace the t and c with their corresponding values. So producing 30 tables and 40 chairs yields the highest gain of $4,100. The second approach in solving the optimal solution is the corner point solution method. The idea is that the optimal solution lies at the corner point or extreme point of the feasible region. There are 4 steps. First, graph all constraints and find the feasible region. Second, find the corner points of the feasible region. Third, compute the profit or cost at each of the feasible corner points. Fourth, select the corner point with the best value of the objective function found in step 3, for this is the optimal solution. Since we have already identified the feasible region, we can now go to the next step, which is to find the corner points of the feasible region. For the Flair Furniture example, the coordinates of 3 corner points are obvious from observing the graph. These are point 00, point 50, and point 080. Next, we need to compute the profit or cost at each of the feasible corner points. The fourth corner point is where the 2 constraint lines intersect, and the coordinates must be found algebraically by solving the 2 equations simultaneously for 2 variables. In order to compute the fourth corner point, we will use the elimination method. We first need to choose a variable to be eliminated. By the way, this is the method used in the isopropyl line solution method on finding the coordinates of the last point. So in this problem, we will eliminate variable t. And to do that, the values of t on the two equations should be the same but at different operations. With that, we need to multiply the second equation, the painting and varnishing constraint, with negative 2. Now we have an equation of negative 4t minus 2c equals to negative 200. Then add it to the first equation, giving negative 4t minus 2c plus 4t plus 3c equals to 240 minus 200. Now the variable t has been eliminated, resulting in 1c equals to 40 or c equals to 40. Now that we already know the value of c, we can now substitute the value in either of the original equations and solve for t. Let's use the first equation. When c equals to 40, then 4t plus 3 times 40 equals to 240. 40 plus 120 equals to 240. Transfer 120 to the other side, giving 4t equals to 240 minus 120. 4t equals to 120 divided by 4, t equals to 30. Thus, the last corner point is 30, 40. Lastly, we need to select the corner point with the best value of the objective function found in step 3. So we made a table which shows the profit of every corner point in order to easily differentiate them. With that, the highest profit is found to be $4,100, which is obtained when 30 tables and 40 chairs are produced. Regardless of the method that we have used, we have arrived at the same highest profit, which is $4,100, and is obtained by producing 30 tables and 40 chairs. So that's all for isopropyl line solution method and corner point solution method. Thank you!
Good day. I am Anthony Joel Salazar, and I will discuss about the slack and surplus resources and the 4 special cases and sensitivity analysis in linear programming models, the graphical method. First, what is a slack? This is the difference between the left-hand side and the right-hand side of a less than or equal to constraint. Often, this is the amount of a resource that is not being used. For example, basing on the Flair Furniture Company, they have decided to produce 20 and 25 tables and chairs respectively. To get the slack, we will subtract the amount of resources used, 155, from the amount of resource available, which is 240. So the slack would be 85. Next is the surplus. It is the opposite of slack, as it represents the amount by which a minimum quantity is exceeded. Basing again on the Flair Furniture Company, they have decided to produce 20 and 25 tables and chairs respectively. However, the total number production of tables and chairs combined should be at least 42 units. To get the surplus, we will subtract the minimum amount, 42, from the actual amount, which is 45. So our surplus is 3. Let's move on to the 4 special cases. These are the cases and difficulties that arise when we are using graphical approach to solving linear programming problems. The 4 special cases are invisibility, unboundedness, redundancy, and alternate optimal solutions. Let's discuss them one by one. Invisibility is a simple problem that arises when there is no feasible region found because of the presence of conflicting constraints. Let's take these constraints as an example. So if we are going to plot the constraints, the graph would look like this. We all know that the feasible region must satisfy all the constraints. However, based on our graph, there are 2 separate regions. Hence, there is no feasible solution for this problem. Next is the unboundedness. This case happens when there comes an infinite solution or open-ended solution. For an example, consider this equation to maximize profit and subject to these constraints. If we will graph them, it would look like this. As we can see, the feasible region is not bounded by any constraint line. With this, if we will try to solve it using the isoprofit line method or the corner point method, the list would be very long and our solutions will never end. Special case is redundancy. This case happens in the formulation of constraints that results to a redundant constraint that does not affect feasible region in any way. As we can see in the graph, the third constraint x of 1 is less than or equal to 25 is redundant and unnecessary in the formulation and solution of the problem because it has no effect on the feasible region set from the first two more restrictive constraints. The last special case is the alternate optimal solutions. This case occurs when the objective function line is parallel to a binding constraint. Graphically, it happens when the isoprofit line runs parallel to a constraint in problem which lies in direction in which isoprofit line is located. In other words, it happens when they have the same slope. In this example, at the profit level of $12, isoprofit line will rest directly on top of first constraint line. This means that any point along line between corner points 1 and 2 provides an optimal x of 1 and x of 2 combination. Let's move on to the sensitivity analysis. It provides a range of feasibility over which the choice of alternative remains the same. Sensitivity analysis offers a better understanding of the problem, different effects of limitations, and what-if questions. We have two approaches, the trial and error approach and the analytic post-optimality method. Trial and error approach usually involves resolving the entire problem, preferably by computer. Each time, one input data item or parameter is changed. It can take a long time to test a series of possible changes in this way. On the other hand, the analytic post-optimality method is done without resolving the whole problem. It examines changes after the optimal solution has been reached.
As the head of the Yomer's Bake Shop, Czarah must decide the daily production totals of the celebration cakes with two flavors, the Ultra Chocolatey Yummy and the Yama Yummy Special. The profit on the Ultra Chocolatey Yummy cake is 150 pesos per cake, while Yama Yummy Special's profit is 130 pesos per cake. Each cake goes through two phases in the production process. There are 120 hours available at the baking stage. On the other hand, 100 hours are available at the finishing and designing stage. Each Ultra Chocolatey Yummy cake requires 30 minutes of baking and 20 minutes of finishing and designing. Each Yama Yummy Special cake requires 25 minutes of baking and 25 minutes of finishing and designing. The company has also decided that the Yama Yummy Special must comprise at least 30% of the total production of both cakes. Czarah's problem is deciding the best possible combination of Ultra Chocolatey Yummy and Yama Yummy Special cakes to manufacture to arrive at the maximum profit. With this, she is asking for your help in solving her problem by formulating it as an LP problem.
To come up with the optimal solution, we need to formulate a linear programming problem and solve it to find the one that gives the maximum profit. So, here's the table that contains all the information we need that will help us formulate a linear programming model. Since we have completely understood the problem, we need to define the decision variables. With this, we let C equals Ultra Chocolatey Yummy and Y equals Yama Yummy Special. The objective function is maximize profit, which is equal to 150C plus 130Y. Our objective function is subject to the following constraints. First is the baking constraint, which is denoted by 1/2 c plus 5/12y is less than or equal to 120. Second is the finishing and designing constraint, denoted by 1/3 c plus 5/12y is less than or equal to 100. To get our third constraint, we will write the inequality y is greater than or equal to 0.3 times c plus y. We have used the greater than or equal sign to represent the word at least. The next thing that we will do is to subtract y from both sides. This will result to 0 is greater than or equal to 0.3c minus 0.7y. Since we need to use addition in our constraint, we will negate the whole equation and it will result to negative 0.3c plus 0.7y is greater than or equal to 0. This will be our third constraint. And we have our non-negativity constraint, which is c and y is greater than or equal to 0. This is now our linear programming model. Note that the 1/2 and 1/2 c is derived from the 30 minutes required time in baking for the ultra chocolatey yummy, while the 5/12 is the required time in baking the Yama Yummy special. Also, the coefficients of the finishing and designing constraint are derived from the required time in finishing and designing stage of the two cakes. Let us now plot the constraints and make the graph. For us to be able to draw the constraint line on constraint 1, we will assign values to c and y. First, we will get the value of y by setting the value of c to 0. So, 1/2 times 0 plus 5/12y is equal to 288. To get the value of c, we will set the value of y to 0. 1/2 c plus 5/12 times 0 is equal to 240. Now that we have the first coordinates of c and y, we will plot them on the graph. As we can see in this graph, the first constraint line can be seen, denoted by line 1. We can see that the shaded region is wide, but we expect that it will be more restrictive when we add the other constraint. For the finishing and designing constraint, we will do what we did with our first constraint. First, we will get the value of y by setting the value of c to 0. So 1/3 times 0 plus 5/12y is equal to 240. To get the value of c, we will set the value of y to 0. 1/3 c plus 5/12 times 0 is equal to 300. We are now ready to plot the points in the graph in addition to the constraint 1. The graph will look like this when we add the constraint line of the finishing and the designing constraint. As we approach to the last constraint, we will be able to identify the feasible region. So let's go to the last constraint. As we can see on the third constraint, we can anticipate that our dividend in solving for the values of c and y will be 0. We all know that when we divide 0 by any number, will result to 0. So we can safely say that the values of c and y is 0. Let's plot it in our graph. We see that our shaded area is bounded by our constraint lines, and we can now identify the feasible region. So, we can now proceed in solving the optimal solution. It has been discussed earlier that we have two methods in identifying the optimal solution, the isoprofit line method and the corner point method. In this problem, we will use the corner point method. Now this is the final appearance of the graph. It is noticeable that we have 4 corner points. We will use these corner points to solve for the optimal solution using the corner point method. So here's the table that contains the profit of every corner point. With this, we can clearly identify the corner point that can give the highest possible profit. We have found out that the maximum profit is 36,720 pesos and is obtained by producing 120 ultra chocolate yummy cake and 144 yummy special cake.